Welcome. Today I will show you how you can build your own GenAI assistant which implements a RAG pattern, and not only that, I will show you everything from how you can scrape data, how you can put it in a knowledge base, how you can build an API around your assistant, implement the assistant itself, build a quick front end to test your assistant, and even build a framework for evaluating the answers of your assistant. So if you're tasked with building some kind of RAG or GenAI assistant at your company, or you want to build your own product, you have come to the right video, because I will show you how to do everything from scratch in a production grade way. This is not some clickbait. I promise you, you can scale assistants you build like this to production. You're probably asking, like, why would I trust you? Like, you can say that, yeah, you don't necessarily have to trust me, but let me just say I have a lot of experience with building GenAI assistants. Right when the ChatGPT API came out, I built something called Scrapy, which is a mental health GenAI assistant, and it is capable of helping you with your mental health. It uses a knowledge base with a lot of psychology manuals in the background to aid it in its answers, and it was also part of my master thesis, which also eventually got published. Not to flex, but it got 10 citations, which I'm very proud of, and I also got to present it at a conference in South Carolina. The paper itself was more about personalization of GenAI assistants, but it definitely used a RAG pattern. I also implemented some other GenAI tools, for example, this product, which you can also find, you should probably search for on my GitHub for this, but it's capable of doing code reviews of your entire project. It uses also a GenAI assistant as the back end. And even like my job is literally just building everything that has to do with natural language processing and AI. So GenAI assistants are a huge part of that. And we have already built a lot of GenAI assistants. So yeah, you could say I have some experience with building GenAI assistants. And in this video, I want to bundle the main things that I've learned over the last few years building these applications. So what exactly is RAG? It's a solution to the problem of how can we add new knowledge to our assistant without retraining the LLM? Because the LLM, it went through a pre-training phase where that's seen a lot of knowledge, but it isn't trained on, for example, your specific company data, or let's say you're building a video game and you want an AI that has some knowledge about the video game world you're building. Of course, it isn't trained on that. So how can we add new knowledge to our assistant without having to retrain the entire LLM? And RAG is a pattern which you can use to solve this problem, and it is probably used in almost, I think, most of the GenAI assistants that are currently deployed. If you already have watched some videos of mine, you know that I also often like to do fine-tuning. So the question often is when to fine-tune, and fine-tune is like retrain your LLM to get knowledge, or when to use a RAG pattern. The first thing I can already say is in most cases you probably want to do both, and I will probably make an entire video about this topic because it's quite large. But in general, RAG is definitely a good pattern to start, and you know when it fits your application, when, for example, the knowledge very often changes. Let's say you want to build a assistant that helps your employees at your companies with asking questions about internal documentation, and the internal documentation changes often. New pages get added, some get removed, some get modified. So if the knowledge changes often, you probably don't want to fine-tune on that every day. So that is already a good sign that you should probably implement a RAG pattern. Also, fine-tuning requires a lot of training data. You need a lot of structured conversations in which you demonstrate that the AI is conversing about the knowledge that you want to ingrain in the AI. But with RAG, you don't need any training data, you just need your raw knowledge, which can just be raw documents. So yeah, no training data necessary if you want to use a RAG pattern. Fine-tuning is also expensive. GPUs are not cheap, and definitely not if you want to retrain a LLM, which can be quite large. And also when fine-tuning, the LLM itself really becomes specific to that application, so you can't reuse it for other applications. And if you are, for example, working in a company, you probably want to reuse your LLM deployment for multiple applications. So then it's also, becomes quite difficult if you fine tune on that, because then you need to have separate deployments for every application. When to fine tune, if you want to have some extra performance, if you want to teach the LLM to perform new tasks, which is probably quite fake, and if you want to use local models. But I'm gonna make an entirely separate video about when to use RAG and when to use fine-tuning. In this video, we are going to use RAG, so you can see if this fits your application you're trying to build. And it probably, I guess it will. So before watching, if you are new to GenAI, you have never built an assistant, or you have built some assistants but they don't scale very well, and you're just watching some Langchain tutorials, well, you're probably crying. I can understand that. And after this video, you've completely leveled up. You know everything you need to know about how to start implementing your own GenAI applications, and I can imagine you feel quite happy and strong and powered up. So for this tutorial, what kind of assistant are we going to build? We need something where we can, of course, ask questions about some knowledge base. We are not going to do anything boring, like, for example, generating some internal documentation or something like that. So what we are going to do is basically build our own AI Pokédex, which can answer questions about everything related to Pokemon. For example, which moves a certain Pokemon learns at a certain level. Why? Because Pokemon is of course very cool, it's not nostalgic. Who hasn't? If you haven't played things like Pokemon Leaf Green or something like that in your childhood, you are missing out. And also I do have some quite cool Pokemon cards. Let me show you. For example, this card right here. Do you know how much it's worth? Well, it's quite expensive, and I literally traded it on the playground when I was a kid. Probably gave some shitty EX card for it, but as a child especially, I did like Pokemon. So let's build an AI Pokédex, which I think will be a very fun assistant to build. We have 5 different parts in this video, and the first part will be about the theory behind RAG. So I can imagine you might be falling or starting to get sleepy a bit, but don't worry, because there will be some Python coding very soon, and I will also share all the GitHubs. So don't worry, and try to follow along a bit with the theory part, as it will help you understanding everything else. So we are basically going to explain the RAG flow that we are going to implement. So if you are familiar with RAG, this will be very familiar with what you already know, and otherwise you will probably learn a lot of things. So what's basically going to happen is we have a front end through which you can ask questions. So for example, you ask in a front end, what is the type of Charizard? And it should be passed to an assistant, which can then, based on a knowledge base which contains Pokemon knowledge, and an LLM formulate an answer. And the flow that we are going to implement is going to be as follows. So through our front end, you ask, what is the type of Charizard? The front end, of course, needs some way of connecting to our assistant. So we are going to build an HTTP server, which is, for example, as this endpoint, and passes in its body a conversation, which at the moment just has the user question, which says, what is the type of Charizard? So this is going to arrive at our assistant, and the first thing the assistant is going to do is go searching for relevant documents. We are going to implement a hybrid search pattern. This is a bit advanced, but I never said like that we are going to build a basic assistant. I said we are going to build a production ready assistant. And a hybrid search consists of both semantic search, which was initially often the only search method that was used with RAG assistants, and is also going to use keyword search. Let's first explain keyword search, as is probably the easiest to understand. What keyword search is going to do, it's going to look in our knowledge base and search for documents which, for example, literally have a lot of common words with the query. So we are literally going to look for Charizard or the word type or even what is. It's probably not only going to look at the literal words, but we can, for example, also look at what is called n-grams. So for example, this is a 2 gram with 2 words together. We can even split one word in multiple tokens. But what it comes down to is we are literally going to search for documents that have a lot of really syntactic similarity with the query. And so we are going to do this, and this is implemented with something that is called PM25, which is a very common keyword search algorithm. If you know about TF-IDF, it's very similar to that. And our keyword search query is going to return a series of documents. Each document will contain both the text of the document, which should contain some information about each Pokemon. It will also contain a URL, which is where we scraped this document from, and will also be returned in the answer, such that the user of our chatbot can verify whether what the chatbot has said was indeed true. And it will also return a score, which represents how much confidence BM25 has in that this document is indeed relevant to the query. But we're not only going to do keyword search, because like I said, it literally looks for syntactic similarities, and we might miss a lot of relevant documents that way. So we are also going to do semantic search, and this is not going to literally look at the words themselves, but will look more closely at the meaning. For example, if we in our query say, for example, fire, let's just say like we literally search for fire, we don't only want to get documents that contain the word fire, but for example also documents that contain the word flame, or maybe what are some more ignite, or some other things that have to do with fire but are not literally fire. And the way to do this is by using semantic search. And we need a method of converting this, of course, to its meaning. And this is done by using an embedding model. And an embedding model is also part of the transformer architecture. The right part, which I put a cross through, is the decoder part, and actual LLMs are just not only just, but mainly stacks of decoder blocks on top of each other. So ChatGPT is the right part, as it can predict next tokens, but the left part is the encoder and can basically turn a sentence into its meaning, and the meaning will be represented by a vector, and the vector has a lot of numbers because of course we can only, the easiest way, of course computers need to work with numbers, so we need to turn our words into numbers, but these numbers are very special in that if we were to plot them, for example, this is the vector of document 1, which for example contains the word fire, and if we also pass the word flame through our embedding model, it will, if the embedding model is any good, the vectors will be very close to each other. So we can calculate something like the cosine, which of course if the cosine is 1, the vectors are very close. So this is basically what an embedder does, turn each sentence in a vector, and then we can do some distance metric on these vectors, for example the cosine distance or cosine similarity, and then use an algorithm such as k nearest neighbors or its approximation, which is also called FICE. FICE is a way to search for approximate nearest neighbors, and then just return the documents which are also passed through our embedding model, and return the documents which are semantically the closest. So this will also return some documents, same as with the keyword search. It will also contain the text, the URL, and a score, which is basically represents the distance metric between the query and this document. And what we then need to do to implement our hybrid search, we basically need to merge documents that were returned here with the documents here, not like merging the literal text into the document, but just picking the 3 documents from these 6 documents, for example, which have the highest score. So that is exactly what we do here. We just take the documents that have the highest scores, and now we have a collection of documents which contain both good documents with keyword search and with semantic search. And yeah, this works better than just using either or. So if you want to implement a RAG assistant, definitely look at hybrid search. So now that we have our documents which are relevant for answering what type Charizard is, you are going to call an LLM. Your assistant is going to, with a prompt, which first of course introduces the assistant that it's an AI Pokédex who should answer questions about Pokemon, that it also should base its answers on the retrieved sources only, because otherwise it's just going to use its own background knowledge, which you probably don't want in the RAG assistant. It depends of course a lot on the application itself, but usually you only want to answer things based on your knowledge base, and also return the URLs of the documents it's used in its answer, such that the user can manually verify it. It will then contain the user question in this LLM prompt and your documents themselves. So now the LLM has everything it needs to know to answer this question based on these documents, and if these are not sufficient, it should just return a standard answer. So we send this to an LLM, and the LLM will give an answer like Charizard is a fire type Pokemon, if this of course can be found in our documents with the used resources, and our assistant is then going to pass this to a front end. So in short, what RAG comes down to is automatically constructing a prompt to an LLM based on documents you fetched from a knowledge base. So in theory and in concept, this is all very simple. In theory, it all sounds very easy, and you also see that the implementation initially is very easy. It can be quite hard to actually get it all right in all the details, but this project will form a very good base for actually implementing something really good. So let's now go over to part 2, which has to do with everything concerning the knowledge, because of course we need to have some kind of Pokédex knowledge base we need to fill up with Pokemon knowledge. So the first thing is, of course, we need this Pokédex knowledge. And to do this, we are going to scrape Pokemon DB, which is a very useful website I found, which literally contains everything we want to know about each Pokemon. If you go on this website, you can see it contains things like which type it is, how we need to breed it. Let's actually just go to the website, might make it a bit more clearer. So let's go to Pokédex. The website is, okay, I was already on Pokédex. Let's go to all Pokemon. Let's say what would be my favorite Pokemon, Gengar, of course. So you can see in which generation it was introduced, how some training characteristics, what its base stats are, what the evolutions are, the actual Pokédex entries into different games, also what moves it learns at every level, and if this is different each generation, some more information about the sprites themselves, where to find Gengar. So we can see that this is a very good website to search for everything. And if you go to the robots.txt, which is, if you are scraping websites, this contains the things you have to respect so you don't get banned. And it says like that you need to wait 2 seconds before fetching each page, and also gives us a very handy sitemap, which we can first off scrape this page and then use this to extract all the other pages we want to scrape. So everything that has a Pokédex prefix is probably going to be something we need to scrape. So this website is very friendly for scraping, which is of course awesome, as we need something like this, and without or a data source we are basically nothing. And of course we also need some kind of database. There are a lot of options, but the 2 main functionalities we need is semantic search and keyword search. Nowadays most these are often called vector databases, but they also support keyword search nowadays. There are a lot of them, like really a lot of them. The way I would choose a knowledge base is just like I say here, just use what your main cloud provider offers. If you're using AWS, use OpenSearch. If you're using Azure, use Cosmos DB, I think this is called. If you're using Google Cloud, use Vertex AI search. And then you also have these like Pinecone. I've used this to power my my mental health chatbot. You also have these 2, and for this video we are going to use Zilliz, not for any particular reason, but mostly that it has a good free tier, and I don't want to pay anything for this, at least because it's just a test video. I believe Pinecone also has a free tier, Weaviate also, but let's just use Zilliz. If one of you of Zilliz is watching this video, please send the money to me that you get from people signing up for your platform. But yeah, I've used Zilliz for my video. We also need an embedder, of course, to both embed the query when searching our knowledge base and also to embed the documents that are stored in our knowledge base. There are a lot of different embedders that are often used. Something like BERT is very old school, and you also have to host, this is something like that you can host locally on your PC if you are looking for self-hosting. Maybe also check out like Roberta, which is the improved version of BERT, but this is pretty old school. You also have these embeddings from OpenAI or of Google Gemini. If you're looking for which embedding is actually the best. There is actually a leaderboard right here, which tracks on a wide variety of tasks which embedder performs the best. So last time I checked, we need to have order it on retrieval. But yeah, last time this also wasn't working. Hugging Face switched to a different way of displaying all of this, and now the ranking is a bit broken because we want to use this for a retrieval task. So you should look at retrieval scores. And as you can see, the Gemini embeddings are scoring very, very good here. Lately, Google has been dominating almost everything in regards to LLMs, but you can also see like these Qwen embeddings might be very promising. Qwen is open source, I believe, as you can see on Hugging Face. This is a pretty small model, only 600 million parameters. So if you're looking for self-hosting, this might be a very good model. I'm not going to inspect everything, but you can, even the OpenAI embeddings like text embedding 3 large are on here. Although, according to at least these benchmarks, the Gemini embeddings are very good. But if you want to have the best embeddings, just look at this leaderboard, which should give you some indication. It of course always also depends on your specific documents, which language your documents are in. So it's not necessarily that the best performing model on this leaderboard will also be the best performing model for your data. And that's also true with LLMs and everything in regards to GenAI. Just, you always need to test it on your own data. But for our video, we are going to use the Gemini embeddings because we are once again not willing to spend much money, and they have a very, very good free tier for a lot of their models. As you can see, we can do 1,500 requests per minute, and it is free of charge. I do believe that it's not always available, so I wouldn't count on this in a production setting. In a production setting, definitely pay for your models, and this text embedding 004 is also a bit, is I believe a deprecated model a bit, so definitely use something different, but it will show us the concepts of everything. So what we are now going to build very soon in Python is the following job. And this will start from our knowledge, the raw knowledge, and eventually we'll insert it in our knowledge base. So we just start from the Pokémon database website, and we are going to scrape it using a Python library which is called Scrapy. I believe you also have some other Python libraries like Playwright or things like Selenium, but Scrapy is a very good library, so I'm going to use that. It's going to fetch all the pages we need. It's then going to clean them and convert them into markdown, which is a very useful format for LLMs and is also more human readable than HTML. So we are going to clean the raw HTML pages, probably also throw some headers and footers which often appear on these pages, and throw them out because it just pollutes the context window of the LLM, and we only want to fetch the relevant information that will help us with eventually answering questions. We then also need to have a chunking step, which the main purpose of this is because each embedder has a maximum input size. We also need to make sure that each document can actually fit in the embedder, and as documents can become quite large, longer than the maximum input size, we basically need to chunk the document, this is called, into pieces which of course still contain enough information but also fit within the context window of our embedder. So we are also going to do that, which can, for example, result that the Squirtle page gets split into 2 chunks. Then we are going to embed these chunks with our chosen embedder. So we get a vector of embedding, a vector embedding like this. And then we are going to insert in our knowledge base both the vector embedding, which will be used for semantic search. We are going to ingest the markdown itself and some metadata such as the HTTPS. So this is going to be one entry in our database, which, as I said, we are going to be using the Zilliz knowledge base, and we are going to ingest each document that we scraped like this. So now let's dive into Python. Let's go over our code and basically fill up our knowledge base. Okay, so let's get started with setting up everything, both our scraper and our knowledge base. I'm gonna start from a empty knowledge base and show you everything that needs to be done. The first thing you need to do is generate your own Gemini API key, which allows you to use all these embedders and things like that for free. At least most models can be used for free. For example, when you hover over one of them, you can see here that with this Gemini 2.5 flash preview, you get 10 requests per minute and 500 requests per day. The older models will have some more rate limits. So for example, with Gemini 2 Flash Lite, you get 30 requests per minute and 1500 per day. But also for our embedder, we basically need this. So what you need to do is go to, if you don't know it, Google AI Studio, click on it, and click here, get API key, and then click here, create API key, and you will have to create a Google Cloud account for this to set it up. So you probably also, this will, if you don't have a Google Cloud account, this will probably show a link to create a Google Cloud account. And if you don't already have a Google Cloud account, you probably need to go to Google Cloud first, create one, create a project in Google Cloud, and then your project will show up here, which allow you to create a free API key. You will then need to go to Zilliz, because that's where our knowledge base will be hosted. Click login. We are also going to log in with our Google account. Okay, what you then need to do is create a cluster. We can do a free tier. We are going to name the cluster Pokédex, and we are going to choose the Google Cloud provider. We can't choose a lot because we are just in the free tier. But anyways, let's just create it. This will show me my password. I'm just going to download this. Don't think we need to do anything with it right now. But we need to wait a while before our our collection is created. Okay, so we have created our cluster, and now we need to create a collection for our knowledge base. The first thing you need to do is, if you download this Pokédex scraper repo, is you need to set up your envars. So yeah, I'm not going to show you my envars, but what you need to do is create a .env file in the config directory. Just copy this env example, which will show you which API keys you need to fill in. The Gemini API key you can get right here from the Google Cloud dashboard. The Zilliz cluster public endpoint will be this, which will be shown on your cluster. And the token, which will be this one, which you also need to copy and fill in here with token. Of course, I can show you my values, but you know which ones you should fill in. Okay, so now the first thing we are going to do is actually set up our Zilliz cluster in such a way that we can do hybrid search. And for this, we need to create collections. So I've created this script. You can also create things like this by just clicking in the Zilliz UI and creating collections right here, but of course that isn't very easy to share, and is also not a very good practice in production. In production, probably use something like Terraform, but a script like that is also fine, because you can just execute this one and you will get the same deployment. So now that we have created all our secrets, we can initialize a Milvus client, which will allow us to connect to our cluster. For each document, we need to define which fields we are going to store in our knowledge base, which will allow us to search for the document, but also should contain the information we want to retrieve about the document. So let's create a schema, and to each schema you can add fields which then represent what we want to store. The first thing is an ID, which is necessary for all documents. They need to be uniquely identified. We also add a vector, which will in this case be the embedding vector, which will be produced by our Gemini text 004 embedding model. This model has an output dimension of 768, so it will produce a vector of 768 numbers. It's very important, if you're using a different embedding, look up how much the output dimension is and pass it right here. We also want to add metadata, which will be a JSON. We also want to add the actual text of the document. And we also, of course, want not only to enable semantic search based on this vector, but we also want to include keyword search, and this will be done with sparse vectors. And the sparse vector, we need to add it to our schema, and we also need to add a function to the collection to turn our text into sparse vectors. So here we specify that we want to turn the text field into a, take it as input for this function and store the output in the sparse field. It might be a bit confusing that for the embedding, for the semantic embedding, we are doing the embedding ourselves, but for the sparse vector, which will be used for keyword search, we are letting the knowledge base itself do the embedding for the sparse vector, but these are just some implementation details and something that Zilliz offers, so you shouldn't pay that much attention to it, that it's always done like this, but yeah, it's just done like this in Zilliz. Okay, so then we need to call this function to prepare all the index parameters. We are going to create two indexes, one for vector search and one for this, that are both vector searches, but vector will be for the semantic search and this will be for the keyword search. So we actually create two indexes. This is also a Zilliz kind of thing, that you can't both search semantically and using keywords on a single index. No, you actually need to create two indices. Here we also specify that we indeed want to search with this BM25 algorithm. And then what we can do is use all these indices to create a collection. So let's execute this script and see if everything is working. I believe this is going to take a while. Okay, no, it finished. Let's see in our UI if something is created. Collections Pokédex. Indeed, we see that our schema is defined here, and that we have two indices, one for keyword search and one for semantic search. So everything here is set up correctly. So we are going to scrape using Scrapy, which is one of the most popular Python scraping frameworks, as I said. It's probably, if you are new, it's probably worth looking at the documentation a bit, as it does a lot of things internally. So I will step through the code, but you will see that you need to know which methods you need to implement, because it will automatically invoke some things, and if you don't know these things, it can be confusing at first. But what we are now going to do is step through this code and basically scrape the entire Pokédex. So let's launch our debugger. The first thing we are going to do is initialize some settings, which should usually be put in a settings.py file. What this says is that we are going to obey everything that is being put in this robots.txt file from the Pokemon DB, such that we are not doing anything that will get us IP banned. We also set a download delay equal to the crawl delay, such that we aren't actually fetching pages too fast. Okay, so we just initialize our crawler process, this is called, with these settings, and then we are going to make our spider crawl, because the spider is actually going to do most of the scraping. So let's go to the next breakpoint, which will actually be in our spider, and as you can see, we immediately are put into the parse method. And what actually happened was the spider or Scrapy will look at the start URLs class variable of the spider we implemented, and it will start by first off fetching the content of this page, which in our case will be this sitemap, which we found also in the robots.txt, and this will contain all the URLs that can be found on the website. So very handy, so we don't need to make the spider follow different links to eventually get all the pages. A sitemap is also always very handy. So we fetched the sitemap, but this is as you can see in XML format. So we actually want to parse all the URLs that are found on this XML. And the way to do this is as follows. We specify a XML schema, and then we basically search for all the URLs on this page using this XPath, which is a way of parsing XML. It's worth looking into, but it's not. But if you just want to follow this tutorial, it's not essential. So what this basically did was that we now have all the URLs of this page in this URL variable. As you can see, they are perfectly parsed, and we have a lot of them. These URLs not only contain Pokédex entries, but also things like, I don't know what this is about, just information about Pokemon Red and Blue, probably which gym leaders are in Red and Blue, some things about the other Pokemon titles, but we only want to scrape Pokédex entries as we just want to create a Pokédex. So what we are going to do is use a regex on the URL to see if the URL actually is about a Pokédex page. Regex is of course very fast and helpful. So what we then do, if it matches the pattern, which this one didn't, we want to launch a request to fetch this page, and when the page is fetched, we want to invoke the parse Pokemon method, which will then allow us to parse relevant information from this page. So let's just skip to the next breakpoint. So now we finally have found an URL which matched this pattern. Can we see the URL? So this is PokemonDB Pokédex.all. And what we then want to do is, this is still contains a lot of irrelevant information. It contains some header and footer on the page. Let's maybe go to the page itself, which will better explain what I mean. Like, okay, this is also a very long page, which we will probably skip, but it will also contain information like this, all content and design and privacy policy, and also, let's go back to the top. It will also contain everything about this header on top, but we only want the actual content of the page. So that is, once again, we are using XPath to get only the main content of this page. You should if you are scraping some new kind of data, you should probably inspect the raw XML and HTML to check what kind of tags are used to delineate the main content, but we are just getting the main content. Then we are once again going to skip the navigation bar to once again get the main content. Then we are going to create one string out of it. We are going to fetch the Pokemon name, which will be the usually if we are scraping something correctly, will be the last part of the URL, but this time I will be skipping all, as this is not a Pokemon but an overview page. So let's go to the next one where we are actually scraping some Pokemon. It's going to be Weedle, so let's go to the same point. Okay, and now we have successfully scraped information about Weedle in the cleaned HTML. Okay, so like here. And what we then want to do is invoke a item pipeline, which will be automatically done when you define them like this in custom settings. You can define multiple pipelines. If you can also have multiple pipelines and really create a pipeline of pipelines, and they will be invoked in the order of this number, but we only have one. And this pipeline will be used for further cleaning and also for actually saving or potentially ingesting on S3 or some other cloud storage the actual scraped content. I've also put a breakpoint there, so let's go through it. Here we are just going to save the raw HTML in a local folder, so let's save that. So you can see it gets saved under raw Weedle, and as you can see we have successfully scraped a Weedle page. Let's maybe look at what we have scraped. You can see we have scraped all the main content from the Weedle page, which is very nice. Of course, we haven't scraped the CSS, which is responsible for actually doing most of the making it look nice. So we haven't scraped CSS, but actual content is here. And this is still contains way too much information. For example, all these tags and information about how exactly it needs to be formatted. Just a lot of irrelevant information which our LLM won't help with formulating a right answer. So what we actually are going to do additionally in our item pipeline is transform this HTML to a markdown format, which is a format which also contains some structure, but much less, as you will see. So let's save the markdown. So we have transformed this HTML basically to this, which just contains some very basic structure. We can also easily visualize it in Visual Studio like this. And as you can see, this contains the tables are parsed correctly, and it basically contains everything that we want from this page. And Markdown is a format that's very often used with LLMs. We also save some metadata of the Pokemon such that we can also ingest it in our knowledge base, such as the name and the URL. You could probably also do some more metadata, but at the moment we are just going to use these two. So that's basically it. And we are just going to repeat all of that, but I'm not going to walk manually through all of this. So what we are going to do is just launch our script and watch everything be put in the raw folder. Actually, now that I think about it, this is going to take a while. So we're actually first going to explain the other steps of this pipeline and then letting everything run so I can just go eat something in the meanwhile or something. But after we have all this, after we would have scraped everything to the, where is the data folder, to the raw folder, you can see we've already scraped some more Pokemon. What we then want to do is chunk it, like I said, because our embedder only has a maximum size, so we are going to have to create little pieces of our content. And this can be done with a markdown chunker, which is actually one of the only useful things Langchain has ever produced. I will come back to on that later, but what it will do is, let's maybe also, or maybe we shouldn't step through it, but what it does, it just takes the markdown and it's going to split on headers. So first it's going to try to split the markdown on this header to get some smaller chunks, then on this header if that's not present, and then on this one. And if there are no headers to split on, we are just going to use a recursive text splitter, which is just going to look at how many characters a document has, and we specify here that each document can only have our maximum input of the Google embedding model we are going to use is 2048 tokens, and on average there are like 3 characters per token, so we estimate that our chunk can maximum have this amount of characters. So we are first trying to split on headers, and if that's not working, we are then just going to split on the text itself. So let's just run this for the files that we have. Is it already done? Okay, that was much faster than I thought. But you see, we have split our files in some additional pages. We have basically split on a certain header, and each part is cleanly separated. It also contains the actual Pokemon name at first, which will help with retrieval. So this is also nicely split, I think, into actual chunks which are not large enough for which we can pass to our embedder. And the last thing we are going to do is actually ingest this in our knowledge base. We also need to embed it. So after we have created all the chunks, once again going to run it a bit later just to show you this. So maybe let's step through it with our debugger. We just pointed to the path where the chunks are being found. Then we load in the content of a chunk. And the first thing we are going to do is use our embedding model, which in our case is our free Google embedding model. We invoke this with the Gemini API to get an embedding. Okay, so now we have an embedding. Let's see what we got returned. Indeed, it's just a list of numbers of size 768, which we also defined when creating our knowledge base right here. So it's always important to check that these numbers actually match and that we are not, it will probably result in an error otherwise. Then we specify our collection name, which is something I've defaulted here, but we defined this when creating our collection on Zilliz in the first step. So it's indeed called Pokédex. Okay, so that's all good. And then let's just ingest this one. We create our data, which consists of the metadata, the content, and then the Gemini embedding. Let's just ingest this one document. I think it's successfully ingested, so let's check on our Zilliz knowledge base how it is. And you can see indeed we have ingested some data with the, I didn't know shelter, I thought it was with one L, but you can see that we have the moves in it, the actual text, the metadata, the vector which we created with Gemini, and the sparse vector isn't visible, but this should be automatically created by the function we defined. So now I've shown you all the steps that are in this entire pipeline. So let's now just run everything, ingest it in our knowledge base, and then I will return to you. We finally scraped all the Pokemon to our raw folder. Let's see how long it took. I think like more than half an hour, because we were of course respecting the robots.txt file. Let's expect some to see if everything went correct. It seemed to have worked. So what we now need to do is run the chunking job with our chunker. This is probably going to run much faster, at least if we implemented everything correctly. See, like it ran in 1 second. Okay, let's see if we got everything chunked. And now the only thing left to do is actually ingest it in our knowledge base with our ingester. So let's run this. See, let's hopefully not hit any rate limits, else I will have to implement some retrying. So once again, taking a while. I should have probably written a 2-key DM or something around it, such that I can track the progress, but as we're already ingesting some things, let's just wait till it's finished. Okay, I probably misunderestimated this a bit, because it took me like 1.5 hours until this was finally run. And now when we look in our database, we can see that if we go to our collection, Pokédex, that there are 8,688 documents in our knowledge base, and this is exactly the amount of chunks we have created. So indeed all our data is indeed present, and we managed to ingest it correctly. But to make it a bit more user-friendly, let's add some visual iterators over it, such that you can, when you run the script yourself, that you can see what's happening. Okay, so the next part we are going to implement is our actual assistant, which is probably the most exciting part. We now have our Pokemon data in our knowledge base, but of course we also need to implement an assistant which uses this knowledge base and can interact with an actual LLM. Which LLM should we use? If you don't know what to use, a very useful option is once again looking at a leaderboard. There's also one not only for embeddings but also for the LLMs themselves. This is based on human evaluation. Basically, people are given the same output, or not the same, to the same question. They are given the output of 2 different LLMs, and they have to choose which one is the best, and based on this, LLMs gain or lose ELO. So at the moment, the Gemini Pro models are actually preferred the most by users, followed by the O3 models. GPT-4o is once again very good. Also Grok 3 is surprisingly high. And you can also find things like the DeepSeek models. You can also look for different categories. For example, for creative writing, the models might be different than for coding. For example, for coding, often what people really like are the cloud models, and I think they should probably be a bit worse for creative writing. Not really, but depending on the task, you can decide which LLM you can use. But for our video, we are going to use the Gemini models, because once again, free tier is simply so good. I really like that Google has done this. I think this is going to be a very smart move that a lot of people are going to integrate with Gemini, and then the transition to actually paying for the models is very easy, and because they also top the leaderboards, it will then be a no-brainer to switch. So we are going to integrate with a Gemini model. And another thing, if you're new, you probably heard about these frameworks like Langchain, LLamaIndex, Pydantic AI, which all promise you a very easy way to build an assistant. I also fell into this trap, which I can honestly say is really a beginner trap, because like when I was first implementing my mental health assistant, I did just everything with the OpenAI Python SDK that just came out. And then I saw a lot of people talking about Langchain. I went looking for itself, and I was also less experienced as a programmer back then. So I immediately thought, okay, it's a framework. It says it's used by a lot of companies. Just calling the Python API of OpenAI is very immature. I should switch entirely to Langchain, but this was one of the biggest mistakes I've made. I quickly reverted back because with all these, I also used LLamaIndex for a project at work, but we also quickly moved away from it because what all these frameworks do is just abstract away the API calls to the knowledge bases, to the LLM, so you don't really have control over how the answers actually get generated unless you dive deeply into the architecture or like the library itself. So also when your assistant is doing something wrong, you basically have to modify the library itself, which is, yeah, if you need to do that with a library, then the abstraction of the library simply isn't working for your project. And that's also what I feel about these libraries, like the abstractions they offer aren't worth just adopting their approach of building agents. Because as I will show you, building AI agents is also pretty easy. And you have all these cool Python APIs to communicate with the different models. You can also send HTTP requests to all the models. So I don't need another framework just to connect to a database like Zilliz or to an LLM. Also, if you want to support multiple types of LLMs, you can just write an easy wrapper around them and create some abstractions how you want to initialize assistants that actually fit your use case. So these things can honestly just be put into the actual trash can. Like, don't use these, at least in my opinion. If you want to have my full opinion on this, I even created a separate video specifically of what I think about these frameworks, but I just think they belong in the trash can. So we also need a way of letting outside services, like for example our Frontend, communicate with our assistant. So we need to define an API, which is basically a server that offers a certain endpoint, for example a chat endpoint, where people can pass their conversation to our assistant and the assistant will send the answer back. There are two main options of implementing such a chat API. The first one, which I have shown right here, was just the front end has to manage the conversation and we just use this conversation to provide an answer, which I call a stateless API. And you can also implement a stateful API, and here some kind of ID is passed for the conversation and only the last question, and then we fetch the rest of the conversation from some kind of database which is fast to query, for example Firestore if you're on Google Cloud, or DynamoDB when you're on AWS, or some kind of Redis server, and then just pass also just the last answer back. We are at the moment for this video going to implement a stateless API, not because it's better, but because these things like Cloud Firestore introduce some additional complexity to set up this project, and I would just want to keep it as simple as possible to show you these concepts. But just note that in production you probably don't want your front end to manage the entire conversation, and then the front end should just pass some kind of idea. It's also useful to store all the conversations somewhere such that you can later do some analysis on it. So in production, this pattern is more often used. You can also use this, but it just moves more logic for managing the conversations to the front end. So if you like it, you can also just keep using the stateless pattern, which we are going to implement. Also, FastAPI, we are going to use that to implement our API. It's a Python library. It offers very good integration with Pydantic for verifying incoming requests. It also offers very good support for having asynchronous requests, which is also something you want with a production level assistant. And this is just very easy to set up. You can also look at Flask. I have less experience with that, but I've also seen that it's a very good Python framework. So yeah, just pick whatever, but we are going to use FastAPI. So enough explanation, let's start actually implementing our own assistant. Okay, so for our API, I once again created a project, and this both contains the code of the RAG assistant as well as the FastAPI server. We will be first looking at the RAG assistant themselves. But before we can do any of this, once again, just initialize a .env file with your Gemini API key and the Zilliz cluster, public endpoint and token, which are just the same envars as you used with the scraper. So let's look at our assistant. And yeah, this is the implementation of our Pokédex assistant. I'm once again going to step through it by debugging it, so you can clearly see what exactly is happening. So let's start. First, we are going to load in our environment variables, of course, initialize some logging. And what we are then going to do is load in an assistant config, as we want to have our config of our assistant separated from the actual code so that the values are not hard-coded, such that we can also easily modify the behavior of our assistant and the different parts by just having to modify this YAML file instead of actually having to write code. And what does a assistant config consist of? Well, a lot of these things will become clearer when I step through the code, but let's go over them now anyways. First off, it's a assistant config consists of an answer generation prompt, and this answer generation prompt will be the system prompt we give to our LLM to finally generate the answer. So this one really contains the most important instructions. For example, it says behave like an AI Pokédex who can answer questions about Pokemon. Always base your answer on the sources you retrieved. In our case, this is very important. And if you don't want to have any hallucinations that are, you probably will still get some because LLMs aren't perfect. But it's very important that you say that you should only base your answers on the sources retrieved if you don't want to have the AI making up data outside of what you included in your knowledge base. But maybe for your use case, you also want to rely on the internal knowledge of your LLM. So of course, then don't add this instruction, but in our case, we do. And I also say to always include the URLs of the used sources, that he has to nicely format this answer in markdown. And if the answer cannot be found in the retrieved sources, answer with I don't know, so just a standard sentence. Also, we have a retrieval query prompt, and this will basically be used to generate the query which we will ask to our knowledge base. That might be a bit unclear why we need this, but let's say we have a conversation of a few turns, and the first turn is like, asking what is the type of Charmander, and the assistant would answer, well, Charmander is a fire type. And in the next question from the user, he says something like, what does it evolve into? So it's referring to the previous question. Well, we can't really search our knowledge base with the query, what does it evolve into? Because it requires context of your entire conversation for a good search. So I literally just ask an LLM to generate a retrieval query, which can be asked to our rec database based on some conversation we pass. You could probably also just stringify the conversation and pass that, but I feel like just asking an LLM to generate a query performs better. We need to specify both a model for generating the answer and generating the retrieval query. This top B is something related to how deterministic the LLMs are. It basically says that to generate the next token of your LLM, only consider the tokens, because all the next tokens get assigned a probability that that token is the next token the LLM is going to predict. But we literally just say only consider the tokens, start from the token with the most probability and keep accumulating probabilities until we reach a probability of 0.8. So not all the tokens are considered to be generated as next token, but only the ones with a combined 0.8 probability mass. So this makes the LLM a bit more deterministic, and you can tune it down even further if you want the LLM to get more deterministic. And for our use case where we basically don't want the AI to make up any data, it can be helpful to tune down your top P. Then we also have a config for our knowledge base, which says how many documents it should return at each query, which embedding model we are using, and what the Zilliz collection name is of our knowledge base. And I created some Pydantic models for this so that we can, Pydantic models can verify whether what we pass indeed corresponds to, for example, these being strings and the answer generation model being one of these 4 models I've specified. These are all free on the Gemini free tier. The Flash models, the 2.0 models have higher rate limits, so that's why I will be using them for this demo. But you can use whatever you want, and the 2.5 probably have better performance. We can load in an assistant config, which consists of all of these by just pointing to a path, and then this helper method will just initialize this Pydantic model. And if you inputted something incorrectly here, it will literally tell you that, because we are using a Pydantic model. So back to the code, you can see we have loaded in our Pydantic model, which contains the values which we are going to use. And now we can use this Pydantic model to initialize our actual assistant or knowledge base. And a Pokédex assistant, just takes in these parameters, which we also specified in our config. Doesn't do anything special. No, it just assigns them to be variables of the class. I do some additional verification here if it's indeed in the valid LLM models. Also sets the API key and the Gemini client, which will be used for interacting with our LLMs and our embedders. I initialize a list of conversation turns, which is basically the current conversation, and this is also what our chat method expects as an input. So it just expects a list of conversation turns as input, and a conversation turn just consists of the role of that turn, which can be either the user or the assistant, and the content that either the user said or the assistant answered. So we are required to pass the current conversation to the assistant. As I said, the assistant is stateless, so it just takes in a conversation and will generate the next turn. So let's say we are a user and we are asking, what is the type of Charmander? Let's see if, with our knowledge, the assistant can answer this. So let's step into our code. I do some verification to check if the role is indeed, some additional verification if the role is indeed, the last message is indeed a user message, and if indeed some messages are passed, and if not, I return an error. I check if the message's length is longer than 1. Because if this is the case, we are required to summarize generate our retrieval query. But if we only have one message, of course, the retrieval query is just the last message, as there is no conversation to take into account. What we're then going to do is search for relevant information for this user query, which is the question that was asked. What is the type of Charmander? So let's dive into this code. I also created a knowledge base class, which does all the interaction with our Zilliz collection. And the hybrid search works as follows. First, we introduce a ranker, which says how much weight we want to put to the results of the semantic search and how much weight to the keyword search, as it could be for your data that semantic search works a lot better, so you could put this to 0.8 and this to 0.2, but for most use cases, just assign equal weights. We are going to embed our query with our Gemini model. So you can see with our embedding model, we are going to embed the query, and we indeed get a vector of numbers. Then we are going to create a semantic search request like this. We are going to do it's called average nearest neighbors, as we are just going to search for the documents which have an embedding vector with the highest cosine similarity. So these are stored in our vector field, the embedding vectors, and we are going to search for search limit amount of documents. So let's create a semantic search, and we also create a average nearest neighbor search request for the text search, which will be done on our sparse vector field, and this will be done with the BM25 metric. So let's also launch this. And now we can use both search request to eventually launch our hybrid search. We define to how many documents this should be reduced, because this will return search limit amount of documents, this will return search limit amount of documents, but we actually only want to return search limit amount of documents, so we also specify that here, and how to merge the documents is specified by this ranker. Also, we want to get back the metadata of all the documents in the text field. The rest we don't need to return, so we also need to specify that with Zilliz. Okay, so we got some results back. Let's see what we got. Let's look at document number 1. What's in the data? Entity, Pokemon, and indeed we got something from Charmander back, so that's very good, and it already indicates a bit that it's working. But we are going to parse this, all this data that Zilliz returned in something that's actually clearer for our knowledge base. So we are going to, for our assistant, so we are just going to parse it into a Pokédex search result class. Okay. So now we have our retrieved knowledge, which are just these search results. And let's see what kind of results we have. The number 1 result is just literally from Pokédex Charmander. It says something about the evolutions. The second search result is for Charizard, which is of course closely related and could potentially also contain something about Charmander. we once again got something from Charmander, something from the Charmeleon, and all the results basically have something to do. Oh, the last one is about Squirtle, but maybe it mentions like that. Yeah, I'm not going to inspect it that closely, or we might as well do to see why this document was returned. Does it contain something? Yeah, it contains some keywords of Charmander, so yeah, it does make sense that even though that this document is from the Squirtle page, that is indeed included. So now we want to generate an answer based on this knowledge. So let's step into the generate answer method. And what we're going to do is use our answer generation model and pass in our answer generation prompt, which is this prompt that I just showed, had just shown that it should answer based on the retrieved sources. And so this also depends a lot on which LLM you're using. The way to call a OpenAI LLM is different from an Anthropic LLM and different from a Gemini LLM, and this depends a lot on the SDK. So here for Gemini LLMs, we specify the system prompt, which is something that's always included in the generation request and contains instructions how the assistant needs to behave. And then we also pass in the conversation history, which in this case on top contains our actual query. But we are going to refine this request a bit because we also need to include the knowledge that was retrieved. So let's see how we do this. Okay, and there are a lot of ways of constructing a good prompt for your LLM to actually take into consideration the chunks that were retrieved. But what I am doing is I'm first just parsing each of the conversation turns, which are of our own class, into the classes which the Gemini API expects, which are done with these parts. And part is something from the Gemini API. It just expects the conversation to be formatted like this. So we loop through each conversation turn and then transform it into a user content or model content turn, depending on if the role of the message is user or assistant. And what we then do is also create a string from all the knowledge we retrieved. So that looks like this. It just says retrieved. Okay, let's also maybe show this a bit. So it just says retrieved sources and then source 1 with on top the URL and then the text of that chunk, and that for all the chunks we basically stringified this. And we just also additionally include this as a user turn. But you could also, for example, transform the last query of the user to also include the sources and just transform it a bit like saying only answer based on these sources. So there are a lot of methods to do this, but I think the simplest is to just add the sources as an additional message to the conversation, which we are going to pass to the Gemini API. So as you can see, contents at the moment contains now 2 messages. The first one being literally the query that the user asked. I find it a bit hard to see this at the debugger, and the second one will include the knowledge we retrieved. So let's return this and ask our Gemini model now to return an answer. What you can also see that we're doing is I did this retry decorator, which is from a library called Tenacity, which is very useful when writing your own and basically anything that has to do with interacting with LLMs or APIs. And what it allows you to do is it will automatically retry this method if an exception gets returned. And with LLMs, often exceptions get returned, for example, when the model is overloaded or when you are hitting your rate limit or something like that. You basically just want to retry the request instead of returning an error. So for all my requests, I basically retry 3 times, and I also wait some time between each request. And I'm basically doing that for all the methods, such as also this one, which are used to interact with the LLM. And I would recommend you to do the same. Okay, but anyways, let's finally try to generate an answer. And let's see what it answered. And the answer is Charmander is a fire type Pokemon, and it returns the following URL. Okay, that's because it's formatted a bit in markdown, but for the end user this should be fine, and this URL should work. And indeed, it says here Charmander is a fire type Pokemon, and our assistant correctly uncovered this. Let's return it as an assistant conversation turn. I also returned the retrieved knowledge, such that we can really expect what our LLM, what was retrieved from our knowledge base. This this includes all the knowledge, such that we can also use it for evaluation purposes. Okay, so let's add it to our conversation history and log it. So indeed, Charmander is a fire type Pokemon. What we're now going to do is provide an additional question which refers to the previous question. It says like, what is the evolution? And of course, this only makes sense in a conversation. So let's see how our assistant is able to handle conversations with multiple turns. So in this case, we once again have a user turn as our last turn, but this time the amount of messages is actually greater than 1. So what we are going to do is generate a retrieval query, which would basically create a query for our knowledge base based on the conversation. So what indeed, as you can see in our query to the LLM, we say generate a retrieval query for the following conversation with all our terms basically stringified of the conversation. And the system prompt will also be this retrieval query prompt, which I've shown you before. It might be a bit confusing what to put in the system instruction and what to put in like the user instruction, but yeah, you should experiment a bit with that. But I would recommend the general instructions, which always need to pass. You should put that in the system instruction, and things that vary based on some user input, put that in just in the conversation itself. So let's do this and ask it. So let's see what it returned as a query: evolution of Charmander. So this is a very nice prompt, a very nice query, which should be able, when we post this to our knowledge base, to retrieve the correct knowledge. Let's see, retrieve knowledge. What is the top result? Charmander. Also says something about evolution chart. So normally the first result should already contain the answer of Charizard. But let's see anyways what we generate. And return it. Okay, it just returns the evolution chart. So it does correctly do it. I didn't see this, but it contains a bit more information than that we asked for, because it says Charmander evolves into Charmeleon at level 16, and Charmeleon evolves into Charizard at level 36. So it provides an answer. But also, let's now once again ask a new question, but this time something which it shouldn't provide an answer to, because there is no Yu-Gi-Oh knowledge, so it shouldn't be able to answer what is a polymerization. And let's see if it indeed correctly says I don't know. So add it to the conversation, generate an answer, and log that. And it indeed says, I'm sorry, but the definition of polymerization cannot be found in the provided Pokédex entries. So this is all indeed working correctly. But now we also want to expose this assistant to the outside world so that we can eventually deploy it and do some actual useful things with this. And that's what we are going to do with FastAPI. And I'm going to once again go through this a bit. It's just a very simple API provider. What you see right here is what we use to launch it. This is the main file. We create an instance of FastAPI. We add some middlewares. This has something to do with networking, which things to allow. This is very default. We also add something what is called a request ID middleware, which just includes some kind of ID with each request. So this is just for logging purposes. And these middlewares basically get invoked before we actually are going to handle the request. So these can do some things like indeed adding some additional headers or some security things. Then what you need to do is include a router, which will be the endpoint where the answers the conversations can be sent to interact with our assistant. We also add some handlers which define what you need to do when an exception is raised. So for example says that if an HTTP exception is raised, just return this. If a validation exception is raised, return this. But let's just look at the most interesting part, and that's the router. And what the router will do is it initializes an instance of our Pokédex assistant using the same config which I already shown you. And then it exposes a chat endpoint. So all the requests will come in from this endpoint. And let me just show you what happens. Let's first off launch our FastAPI. It is available on port 8000. So let's go to it. And what's also nice with FastAPI is that you automatically get documentation Swagger docs when you go to the docs path. And you see we have a chat method right here, which expects a conversation as input. So yeah, let's try it out. Let's pass a question like, what is the type of Bulbasaur? So you can see we enter our chat endpoint. A ID was injected by our middleware, and I fetch it like this. So I would recommend you to log this to get some traceability. Let's also time the request, and what we just are going to do is invoke the same assistant with our input, which was this conversation that was passed. And the good thing about FastAPI is that we can just define a type hint that is a Pydantic model like this, and it will automatically get parsed into this. So it has a very good Pydantic integration. We then just call our assistant, which I've shown you already before. We get an assistant response back, which says Bulbasaur is a grass type Pokemon. So does it log that? I don't know. We log the assistant's response. This also contains all the chunks, so that's why it's probably a bit unclear, but the response itself was a conversation turn, which says Bulbasaur is a grass type Pokemon and a link, and these search results can just be ignored for now. These are just for debugging purposes. I format an assistant's response, which just contains the conversation turn that contains the answer. And let's return that. And normally now we should see here that, okay, maybe because with the debugger it doesn't work like that. So let's just end the debugger and just normally launch it. And let's ask the same thing again. Okay, and I see that we have some error here. Let's see, a validation error. And I think this is because I did this thing with giving back retrieved results later, because this is mainly used for the evaluation setup. So let's do it like this and unpack it. Let's see if it now works. Indeed, we get a 200 back and it says Bulbasaur is a grass poison type Pokemon and correctly refers to it. So I don't think there's many more interesting things to say about FastAPI and the server. If you're interested in it, just look at the documentation, but it's pretty straightforward. Because we want to build a complete application in this project, we are also going to set up a front end so that we can more easily interact with it when we actually want to try it out ourselves. There are a lot of front-end frameworks. We are going to use Streamlit for this video. It's not really a front-end meant for production-ready assistants, but it's just very easy to set up and test out our Pokédex AI assistant. If you want to put something in production, you would probably use something like React or Next.js, which is a framework built on React. When I build web applications, lately I always use Next.js because I find it very helpful and it's also really easy to implement very powerful front ends. I've also heard about frameworks such as Foo, I think this is named, and Svelte, which is a bit hard to pronounce, but if you are new to front end, just know there are like literally thousands of JavaScript frameworks. It's honestly insane, and a new one comes out every day. So don't be tempted to just switch around in a lot of frameworks. Just pick one. I would say for a beginner, just learn standard React, which is a library made by Meta, and it's also very good. So just learn React or learn something else and just stick to that, because honestly you can implement each front end in almost any of those. But we are going to use Streamlit for now, which I actually learned specifically for this video, and I found out is a very good framework for quickly prototyping applications. So let's show you how I built this. Okay, so let's also build a quick front end to interact with our API so we can have some nicer user experience. I do this with Streamlit, which is not really it's a front-end framework, but it's mostly for prototyping. And I'm also very new to Streamlit still, but what it does offer you is some pre-made UI components. They also have, I just followed this tutorial to create a chat app, but you're not like literally creating, for example, an input field. You are just typing something like, let's see in my code, you're just typing, for example, Streamlit chat input, and automatically a input element will appear. So it's completely different from something like React, where you're really manually almost creating all these elements. No, it are just some pre-made components. All the UI and the layout will be automatically handled for you. So it's very easy to get started. And what my code is just doing is it's keeping track of the current conversation in some kind of session state, which will be just a list with all the conversation turns. This part will just draw the entire conversation, like draw all the chat bubbles below each other. Then on top of this, there will be an input element where people can ask questions to our assistant. And if a question is asked, we format it in a conversation turn the way we expect it in our API. we write it in our as a chat bubble in our conversation, and then we use this conversation history to get an assistant answer by calling our assistant API. Of course, if you're doing this on a different port or you're actually hosting your API, you should change this URL. I also defined that I want a timeout after 60 seconds, and I just include the entire conversation, which is what my API expects. So it's not really that difficult, Streamlit. You can get started with it, I think, in half an hour. So let's quickly run this and see what it's actually all about. Okay, so this is what our UI looks like. Doesn't maybe look that professional, but it's easy to build. So let's maybe ask something like, what do you know about Squirtle? It's indeed running. Okay, it gives me some information, water type Pokemon, tiny turtle Pokemon. Do you know something about the moves? Do you know something about at which levels it evolves? Okay, and indeed correctly found out that it evolves into Blastoise at level 36. Maybe ask some more difficult question. Which Pokemon against which types, against which Pokemon would Squirtle be effective? That requires a bit more reasoning. I don't really know if it knows how to answer this because our assistant is still rather simple, but let's ask anyway. Okay, it indeed knows the correct types against fire ground types. Give me an example of a ground type. Which one is the best? Let's see if it gives me some answer. It indeed gives me some best Pokemon. Some of them are ground type, but I think it took a bit more. It didn't go further on this. But anyways, you can see we can have some conversation about our knowledge, which is already impressive, I think. And it does correctly provide links. And yeah, just using the front end is a nice way to interact with our assistant. We have come to the last part of what we are actually going to implement, and it might be the most, of course, one of the most important parts as well, and that is actually the evaluation of the assistant you implemented. If you're just implementing something for your friends or for yourself, you can just chat a bit with it through the front end and check that what it does is correct. But if you want to actually put something into production and also want to improve your assistant such that it becomes better, then you need a way to evaluate it. And how do you do this? Well, you just ask it, for example, a question, what type is Bulbasaur? To which you have a ground truth. Bulbasaur is a grass type and it can be found on this page. And you just give the question to your assistant. And for example, in this case, if it answers Bulbasaur is a water type and it used this knowledge, then we can say that the answer definitely was wrong because, of course, Bulbasaur is a grass type. What you can also know, for example, by evaluating this is that, let's say we know that the truth can be found on this page, and if this page is indeed retrieved, then we, for example, know that something is wrong with the LLM or the prompt to the LLM because we have retrieved the correct knowledge, but still the assistant is unable to answer. But let's say, for example, that the answer is wrong, but in the retrieved URLs also not the correct knowledge is retrieved, then we know that something is wrong with our retriever. Maybe the embeddings we used are not optimal, or something went wrong in the cleaning step, or maybe the chunking method needs to differ. Maybe we need to do some different kind of search. So you can see that it can also help us not only improve the assistant, but also help to debug it. So that's why evaluation is very, very important if you want to build a production-ready assistant. But we need a data set which consists of questions, the ground truth, and if you're using a knowledge base with URLs, then you also need to include the URL on which the answer could be found. And to get such a knowledge base, the most, probably the best way is if you really have some human experts who are willing to create some questions about the knowledge domain, answer them, and also provide links to where this answer can be found. But of course, we all know that people don't really like to do this job, just creating data sets. So it's probably hard to get a hold of them. They can maybe create some questions, but yeah, you really need to convince them to create a data set of, for example, 1,000 questions. So what I often like to do is just employ an LLM itself, just give it just randomly sample some pages, or at least one page of my knowledge base, for example, in this case, the page of Bulbasaur, and just ask the LLM, can you just generate a question and answer pair about this data? And then we have everything we need to build our data set. However, this approach usually leads to rather simple questions, also often very repetitive questions. So it still requires a lot of work to get really complex questions, and I found out that this is pretty hard to do. So in the ideal scenario, you would probably have some LLM generated questions and answer pairs. You would have some very hard human generated question answer pairs, maybe also some questions generated by the LLM which are then answered by the humans. But yeah, for this video we are just going to employ the LLM tactic and just generate a data set that way. But of course, generating a data set isn't enough. We also need to have some metrics to evaluate this. And if you, for example, look at this, if we ask what type is Squirtle, Squirtle is a water type, and our assistant correctly says so, how do we give it a good score, for example? What kind of scores do exist? A library which implements a lot of GenAI metrics to evaluate LLMs and assistants is called Ragas, but lately I'm kind of switching away from it, and I'm implementing more of these things from scratch. So what I would actually recommend you to do is to first off look at some classic NLP metrics. These come from translation backgrounds, so to check if a translation is right. And just like with our keyword search, where we are using keywords to retrieve documents, here we are looking at keywords to check if an answer is correct. For example, for this answer, maybe if we not put the exact answer, Squirtle, let's see how I can reword it. Maybe something like the water Pokemon Squirtle is of Gen 1. Very ugly sentence, but it can demonstrate what I mean. Then, of course, because both the answer of the assistant and the ground truth contains Squirtle, it contains water, and that way we can see that at least there are some keywords that are both in the ground truth and the answer, so it should probably get a pretty high score. But of course, this is a perfectly valid answer, and there are still some keywords that are not the same. So you should also really look at the meaning of the sentence, and that is where once again AI comes in. And we are going to define a lot of custom metrics ourselves, which will let an LLM judge how good an answer is by outputting some score. And this is basically also what Ragas is implementing. But once again, I think you can easily implement this yourself and have a lot more transparency. So some metrics we are going to implement, for example, could be just judge how correct this answer is by asking an LLM. We can also judge, like, we have retrieved this knowledge. Does an LLM think that the answer is actually grounded by this knowledge? Something that's also very useful is to calculate something like an URL recall to, for example, check if this ground truth URL is actually included in one of the URLs we retrieved, and that way we can really evaluate if our retriever is doing its job. So there are a lot of options, and you can, using AI and things like that, really you should probably come up with some metrics that are specific to your use case, and using LLMs, they will probably be very easy to implement. So let's also create an evaluation framework ourselves. Let's now look at our Pokédex RAG evaluation framework. And the first thing you of course need to do is, once again, initialize your env vars, your mvars, by creating a .env var and fill in these values. Then the second thing you need to do is actually take the raw data you scraped in the scraping step and paste it right here in a raw folder. In a production setting, you probably have all your scraped data somewhere on an object storage such as S3, or I don't know what the Google Cloud alternative is, and not locally. But yeah, we are going to use this raw data to generate questions, so just place it right here if you want to generate a data set. And that's also the first thing we are going to do, is generate our own evaluation data set. So what this code exactly is going to do is we specify how many questions we need, which model is going to generate the questions, where the raw knowledge is based, and what the output directory needs to be. So let's maybe also step through this. So let's start. The first thing we are going to do is, in this raw directory, we are going to list all the directories which correspond to the different Pokemon. What we are then going to do is randomly sample a certain number of directories based on how much questions we want to have, because we are going to ask a question about each directory we sample. Then what I'm doing is I'm creating a thread pool. This isn't essential, but it allows me to speed up things a bit. When you are doing something related to I/O, such as reading files or calling APIs, and all the requests can work independently, you can use a thread pool, which will basically allow you to do these things in parallel. In Python, it is not really parallel, but yeah, that's another, that would dive me off a bit off topic. But anyways, you can set a certain amount of threads, and a higher amount of threads will allow you to do more things simultaneously. But also remind you that we are using the free tier of these Gemini models, so they have a very low transaction per minute limit. So if you put this too high, you're probably going to hit your rate limits. But if you're paying for this, just set it as high as possible, because it will allow you to generate your data set as quickly as possible. And what each thread is going to do is try to generate a question and answer pair based on all the information that we have about this, that we scraped about this Pokemon. So let's continue to the next breakpoint, where we are actually creating a QA pair. We are in this raw directory from the Pokemon we sampled, in this case Kangaskhan. We load the index file we scraped. and the metadata. Then we are going to use our Gemini question answer generator class, which is also something I created. And this is responsible for calling the Gemini API once again and asking it to generate a question and answer pair, which is a question and an answer, of course. Why did I close this? Okay, let's go to the breakpoint again. So what it does is we are, for example, in this case, from a new Pokemon. Which one was it? Pydantic. I don't know this one, probably a newer one. Generate a question answer pair. And how does this work? We're once again going to call the Gemini API with a certain model. And we have a question answer prompt, which by default is set to generate a question and answer pair that is about, okay, this is a typo, but it works anyway. That is about, and can be answered with the following knowledge. Okay, that still makes sense. So basically we pass in our markdown content about the Pokemon, and we ask it to generate a question and answer pair. A bit more interesting is that we are using structured outputs. So we are here saying to Gemini that it should give its answer back as a JSON, which should have this format, so both a question and a ground truth. This is very helpful that we don't have to manually start parsing things. And let's see what it returns. It indeed returns a question answer pair, and it asks something like, what is the national Pokédex number? And it says, yeah, that is the Pokédex number, which can be found on that specific page. So let's just continue, and yeah, that's basically what the code is doing, continuously generating these QA pairs. And at the end, it will just save all of this as an evaluation set and output it here. But I'm just going to manually start it, as I don't want to wait for it. Let's generate like 20 questions. You can see that this goes relatively quickly. Okay, and as you can see, we are hitting rate limits. So maybe because we are poor, not really though, but I just don't want to spend any money. Let's put it to 10 questions and hope we don't hit the rate limits this way. Okay, I need to wait a while. Flashlight. Okay, this one wasn't exhausted yet. As you can see, when you don't want to spend any money, you have to get creative. You could also do something dynamically, like when you get a rate limit error, switching to another model in your code. But let's see which evaluation set we generated. Okay, this one was the one that failed, I think. But this one is correctly. It asks some questions like, what is the base total stat of Dragonair? What is species? Yeah, the questions can be very simple, and that's also the downside basically of using LLMs to generate it, especially if you're using these less complex models which generate, yeah, probably more simple questions. So what you can do to get some more complex questions is, first off, try to experiment with the prompt a bit. Try to, for example, also have multiple prompts, such that one prompt can, for example, ask different things than other prompts about the Pokemon. You could also sample multiple pages at once and ask it to generate questions that involve both pages. So this is an entire this is a lot of work into itself to use LLMs to generate good data sets. So now we can run our evaluation script to evaluate our assistant on this dataset we generated. So that's also why I copied my RAG assistant from the API to this repo as well. You should probably create a package from this, which you can install with pip or something like that, so that you don't have to manually start pasting your code around. But yeah, if you're using this in production, definitely create a package. And what our answer generator will do is it will load in our assistant and will then invoke the assistant to answer all the questions, all the QA pairs of our data set. This code isn't very interesting, just invoking the assistant answers and yeah, parsing the answer. And then when we have this filled in data set, we can then ask a evaluator to evaluate the answers of the assistant. This is interesting, and we can evaluate on these metrics: answer correctness, faithfulness, context relevance, helpfulness, and URL hit rate. URL hit rate is the only non-GenAI metric I included in my in this framework so far, and it will just look at which URLs of the chunks that were retrieved in the retrieval process, and it will just count like because our ground truth answers only have let's see, QA pairs, like all our generated QA pairs have only one true URL from where this question is based. This code will currently just check if this URL is in the chunks we retrieved, and then the hit rate will be 1 and else it will be 0. But if an answer is, for example, if you have data sets where the answer is based on multiple sources, so yeah, you have a list right here, then it will just calculate how many of these you have also retrieved in your retrieval process. So hit rate is definitely important for seeing how well your retriever is doing. And then we also have these GenAI metrics, which are also interesting. And what I'm basically doing is constructing a lot of prompts. For example, to calculate answer correctness, what I'm doing is I give an LLM the question, the answer that the that the assistant gave, and the expected answer. And I basically ask it to output a score between 0 and 5, and also the reason for the score. Same for a thing like faithfulness, which measures like if the answer is actually based on the context we retrieved from our knowledge base. So we once again ask for a score between 1 and 5. Context relevance, whether the context retrieved is actually relevant to the question that was asked. And just something custom like helpfulness, in which I basically ask, is the user who asked the question helped by this answer? And you can define, especially with GenAI, a lot of metrics which better fit what you are trying to measure. And you also have frameworks like Ragas, which just implement these metrics for you. But as you can see, it isn't very hard to write a prompt like this and get an answer back. What you also, what is maybe also interesting for this is, let's see where we're actually asking the LLM, is that we are once again using structured output. So we want our LLM to answer with, just the score and the reason, and it needs to be parsed as a metric score. But anyways, let's run this code. First, fill in the Q&A set, the evaluation set with our assistant, and then have an LLM evaluate it. So let's run. Okay, I put the wrong evaluation set. That was from a previous one in here. Let's see, answering questions. Hopefully we don't hit any rate limits. Okay, our answers are answered. And let's now evaluate it. Okay, and we have our evaluation report. Let's check if our assistant was to correctly answer the evaluation set. Okay, and we have very good scores because the questions were of course very simple. I also write some metadata which LLM was the evaluation model, but we have a perfect hit rate. So for all the questions, our retriever was able to retrieve the URL that we were expecting. Faithfulness is always a 5, context relevance is always a 5, and helpfulness is almost a 5. So let's see what it did. For example, the question was, what is Joltik's species? And the crowd threw this attaching Pokemon, and we indeed retrieve and generate an answer that is an attaching Pokemon, and we also retrieve the correct URL somewhere in the knowledge we retrieved. So let's see what the metrics were. So URL hit rate 1 out of 1. Here are the reasons for the different metrics. It indeed gives a 5 out of 5 for what are these: faithfulness, context relevant, and helpfulness. So, and let's see why this was a 4 for helpfulness. What reason did the LLM give? It doesn't directly answer the question, what is Joltik species, which is the name. The answer is close but not perfect. So you can see, of course, with these GenAI metrics, they are a bit subjective, but they give a good indication of what is happening. What is the base total stat of Dragonair? Answered correctly. Once again, the LLM also thinks it's good. What is Pichu's species? Pichu is a tiny mouse Pokemon. Indeed, this is correct. So as expected, the metrics are good. Okay, maybe the helpfulness here wasn't that good according to the LLM. The answer provides, but it includes redundant information, 2 of the same URLs. Let's see. Okay, yeah, the LLM indeed gave back the same URL twice. So this should be something to be looked at when you want to improve the model. Let's see some other things. At wedge level.fetchling evolve level 17 seems like a perfect answer. Indeed it is. What is Scrap's type? Poison water. Indeed correct. Alcremy's species, cream Pokemon, just straightforward answers. So helpfulness is a 4, what? And includes a link. However, it does not directly answer the question. What? I think this is a pretty direct answer. So I don't get why we get a 4. We're also using a very cheap model, but yeah, a 4 is still very good. What are the 2 forms of Kimighoul? 2 forms, chess form and roaming form. Once again, a perfect answer to me. 5 out of 5s out of the board. Base stat total of Morgan 370. Entirely correct. The base friendship value of Basculin in generation 5 to 7. Okay, 70. It just perfectly repeats the answer. So 5 out of 5s. National Pokémon number of Scissor. Correct one. So indeed, it had a very good score, and at least for these basic questions, it was able to answer correctly. So there are definitely a lot of improvements that can be done with this framework. So maybe some new metrics, a better way to generate questions. Maybe you can set up some questions yourself. But anyways, this gives a very good base which you can improve on to build your own evaluation framework. And the last part we are going to look at, we have implemented everything we wanted, but let's look at some next steps if you really want to go through with this. And which I might include in some future video, but you can also, if you want to go to production or release a product, definitely look at this yourself. We want to also not only run our application locally, so you need to, for example, Dockerize your FastAPI and your front end, which will allow you to easily deploy this Docker image on a cloud platform. And everything in regards to cloud is if you haven't done it yet, it can be an entire learning process in of itself. So this is definitely something that is worth learning. Also, guardrails become very important when you put something in production, especially if you are working around some sensitive topics. And also, just if you put something public, people will try to take advantage of it. They will try to make it curse or say some inappropriate things. So we also need to block certain inputs and possibly also outputs. And once again, if you want to implement this, a very good approach would be to have another LLM judge if the input is actually up to your standards that you expect your assistant to answer on, and return it like yes or no. And if it's not appropriate, then just block the input and return some standard answer. Also, an extension which I will definitely be looking at is how to do tool usage with an assistant, and this is increasingly becoming important. For example, we also might be wanting to allow the assistant to access some things on a Google Drive, or a lot of information might be stored in an SQL database, or we want to make the assistant search on the internet, or we want to make the assistant automatically order an Uber or make some reservation somewhere. So we need a mechanic for making an assistant calling another API. And this is called tool usage and is necessary to create a real agent. I'm probably going to make a video about this very soon, so stay tuned for that. And finally, another thing you can look at is, of course, fine-tuning, which can really also improve the LLM itself and also make the LLM learn a lot of different tasks which it previously could not do. So if you're interested in fine-tuning, definitely look at this video. You can also, using Unslot, fine-tune it for free, so definitely worth checking out. And finally, and maybe the most important thing, is that you really need to iterate on all of this. Just run the evaluation framework, check what goes wrong, improve that part of your assistant. A lot of iteration is necessary to come to a good assistant. It's probably worth it to just not try to release the perfect assistant right from the go, but really release it, collect human feedback, keep running your evaluation framework, and improve gradually. So I hope you enjoyed this video. This definitely was another very large video. I hope I gave you some clear explanation of what RAG is all about. If you're interested in seeing all the code or just replicating what I've shown you, all the GitHub repos are in the description. So I hope you enjoyed this video, and if you're interested in more machine learning, deep learning, AI, GenAI videos, definitely consider subscribing, and I see you in the next one.